All right, last part of chapter 7 has to do with those Y error bars on graphs. Now, you've learned in the lab and by doing class assignment number 3 that these Y error bars, they look like capital I's on, could be a bar graph or a line graph. All right, so these structures here, of course I have a bar graph, but if this was a polygon and we had lines, then you would just see these as well. They look better. I find, I don't know, for me, I like seeing Y error bars. I think they look more attractive on a bar graph, but you know, whatever. Okay, so what these represent are simply confidence intervals. And more often than not, they either represent the 68% confidence interval or the 95% confidence interval. And if they represent the 68% confidence interval, then what we're saying is that 68 times out of 100, the true mean mu, and by the way, this the top of the bar is x bar, right? Remember, x bar is always in the middle. All right. Sometimes I see Y error bars where there's, it starts here and it ends up here, and I know they're wrong because this length here has to be the same length here, right? They have to be right smack in the middle. Anyways, if it's the 68% confidence interval, then we're saying 68 times out of 100, we've drawn the interval correctly, and mu will be somewhere between this value and this value. And if it's the 95% confidence interval, then it's just 95 times out of 100. Now, earlier you learned that the 68% confidence interval just boils down to x bar plus or minus standard error of the mean. The z drops out. Why? Because if you want the 68% confidence interval, that means you're going to use z plus or minus 1. And 1 times any number is this number. So that effectively drops out. So the confidence interval is just x bar plus or minus SEM. All right? Now, why do we put error bars on graphs? Well, it gives us a measure of sampling error. So we can see the typical fluctuation in scores such that we have an idea of where the true mean falls. All right, so we can see at a glance that this group here had the lowest amount of sampling error, and this group here had the highest. We just look at the error bars. And that's going to be true whether it's, we're looking at the 95% confidence interval or the 68% confidence interval. That's true regardless. Now make sure if you're using 68% confidence intervals, make sure that that's true for every single mean. You can't use 95% here and 68% there, etc. You can't mix and match, okay? All right. So that is, that is one reason why we include these confidence intervals, these Y error bars. If they're not on a graph, we call them confidence intervals. If they're on a graph, we call them Y error bars. And we always have to specify what we used as our Y error bar. Was it the 68 or the 95? We have to specify. Anyways, so just by looking at the error bars, I can see how much sampling error was associated with each mean. Okay, now, the other reason is because we can use these confidence intervals, these Y error bars, to make judgments about significance. Now, when we say significance, what we mean is we're going to be able to look at the means 2 by 2 and figure out which ones will, if we were to do a significance test, like a t-test or something else, we'd be able to get a good sense of which means will be significantly different from each other and which means will not be significantly different from each other. Now, these rules only apply, though, if we're using the 95% confidence interval or the 99% confidence interval. If we're using the 68% confidence interval, we could be running into problems. We could be saying, oh yeah, those are going to be significantly different, when in fact they're not. All right, so the rule I gave you initially was that if the two confidence intervals, so the y error bars, for two means do not overlap, the means will be significantly different from each other. All right, that was the rule. So if two means do overlap, then they won't be significantly different. And so if we were to apply that very simple rule, what would we conclude? Well, let's just compare men and women driving down the highway, listening to music, and we want to know, depending on which type of music they listen to, will that affect their speed that they are driving at? And so in the classical condition, if we compare men and women, see how their y error bars overlap completely? So here, if we were to run a significance test between men and women, it would not be significant. In other words, men and women, the mean speeds would not be significantly different for men and women. What about these two means? So men and women listening to rock. Well, here their confidence intervals do not overlap. And so we would conclude that the mean for men is going to be significantly higher than the mean for women. Notice I'm telling you which one is higher and lower. That's important, okay? So always tell people which one is higher, which one is lower. So the mean for men is going to be significantly higher than the mean for women. What about here? Again, these two means do not overlap. So we would say that the mean for women is going to be significantly higher than the mean for men. Now that's using this very, very simple rule. Now I'm going to refine that rule.
So earlier in the course, you learned that if two error bars do not overlap, the most likely reason why the two means are different is due to sampling error plus something else. And if that's true, then if we were to run a hypothesis test to see if those two means are different, that hypothesis test would most likely be significant. But again, that's if the error bars do not overlap. So the opposite is true, right? You learned that if the error bars do overlap, then probably what we're looking at is just sampling error, in which case the hypothesis test would come out to be not significant. Null, none, and nothing, right? The two error bars overlap, so it's probably just sampling error. Well, that was a very crude representation of the general guideline. And what I'm going to do now is I'm going to present you with a refined rule, okay? Because it's not just as simple as I led you to believe. That's what you were ready for initially, but now I think you're ready for the nuances. All right, so what are they? Well, first of all, you need to know, even if the two error bars overlap, it's still possible for the two means to be significantly different. Now I know that comes as a shock because I said, remember, that if they overlap, then they're probably not significantly different. But now again, here comes the revised rule, all right? So when would it be that the two means could still be significantly different, even though they overlap? Well, this could happen if at least one mean is not included in the other group's error bar. All right, I'm going to show you a representation of that, but this is one of the exceptions. Okay, so if one mean, so the mean, let's say for group 1, is not included in the error bar for group 2, then the two means could still be significantly different. Or it might be that that's true for each mean. So you might look at, for example, the mean for group 1. It might not be included in the error bar for group 2. Similarly, the mean for group 2 might not be within the error bar for group 1. All right, that would mean that both means, each mean, is not included in the other group's error bar. Now I know, don't worry, I know this is a little freaky, but I'm going to give you examples. Now there's another way of phrasing the rule. You could say that the two means could still be significantly different from each other if one group's error bar does not include the other group's mean, or if the error bar for each group does not include the other group's mean. All right, so don't worry again, I'm going to be giving you examples. Now, I do have to tell you that this here, using y error bars to make judgments about significance, only really works if your independent variable is between subjects. So that means that there's an entirely different group of people in each level of the IV. If it's within subjects, that means that the same people are tested in each level. And then this rule generally, any rule about using y error bars to judge significance, it doesn't work, at least not as well. All right? Okay, so let's run through some examples. So let's look at this case first, all right? You'll notice that this error bar does not overlap this error bar. The two do not overlap. And if you don't believe me, let's take this one and move it out here. And let's take this one and move it out here. And we'll see it like so. All right, so I didn't change their relative position. I just moved this one to here, this one over here, and you can see that they don't overlap. So when this happens, the means are probably significantly different from each other. So this mean is probably significantly different from this mean. Okay, now let's consider this example down here. All right, so in this example, you can see that the two error bars do in fact overlap. All right, this one here is within this interval, so you can see they overlap. Now, could it still be the case that this mean is significantly different from that mean? All right, so what we're going to do is we're going to look at this mean, right? This is the mean for group 1, and you notice that it is not within the confidence interval of this mean. So you see again, this mean is not in here. That means that these two means could in fact be significantly different from each other. Now let's consider this mean. So if we look here, we also see, hey, you know what? This mean is not within the interval of this other mean, right? This mean is not in this means interval. So here are two reasons why the means are probably significantly different from each other. Because remember, this only has to happen once, right? Either this mean is not in here, in this interval, or this mean is not in that interval. But in this particular instance, we have, it's the case that both means are not in the interval of the other mean, okay? So the means are probably significantly different. Now let's look over here at these next two examples. Okay, so this mean is in this means interval, right? Uh-oh, that could mean it's just sampling error, why the two means are different. It could mean that. But let's look at this mean. If we were to look at this mean, we would see, hey, it's not in this means interval. And remember, this only has to happen once, and the two means could still be significantly different from each other. All right, and again, it's because this mean does not appear in this means interval. Okay, all right, let's look at the last example. This mean is in this means interval. That could indicate sampling error, right? This mean is in this means interval. What about this one? Well, this one is in this means interval. So now we have two situations, right, that are the same. This mean is in this means interval. This mean is in that means interval. So now the safest conclusion, the means are probably not significantly different from each other because both of them occur in the other means interval. All right. So this mean is in this interval, and this mean is in that interval. All right, so what you need to do is you need to play this back and really try and think critically, analytically, about what I've just told you, okay? Don't throw your hands up in the air and say, I don't get it. All right, you have to listen to this a couple of times maybe before it really starts to make sense because the rule is hard and fast. Hard and fast, hard and clear, black and white. All right, there is a very, very definitive rule that we use for using error bars, and judging significance. And so go through this a couple of times, know the rule, and then you will see it applied. All right? Okay, well, that's it. And good luck. I hope this makes sense for you.